Hello everyone and welcome to my talk. Today I'm gonna talk about security by testing and how I try to improve the security of my Go projects just by writing more tests. Before starting the talk, I will give you a little introduction about myself. So my name is Alessio Greggi. I'm a software engineer, full-time cat food opener for my furry friend, and jokes apart, I'm passionate about reading and taking long walks. On the social media, you can find me on GitHub, LinkedIn, Twitter, and so on, with this unique account and this amazing avatar. So let's start the talk. First concept to know is about code coverage. Code coverage is a metric that can help developers understanding how much of their source code is tested and how much is not. It is mostly used when writing a unit test, but not only related to them. And it's expressed as a percentage. Let's go a bit more in depth with code coverage with Golang. It was first time introduced in version 1.2. April 2013, if I remember well. And this support was specifically for unit tests. Here's the link to the announcement. And the story continued after almost 10 years with version 1.20 with a new great support for the integration test. So this means that combining the unit test with the integration test coverage, the coverage percentage of our projects sensibly increased thanks to the last feature. During this time also, the Go community introduced some nice tools, like for example, the Go tool cover that gives you the ability to render the source code with its coverage in an HTML page and so on. So that's what happened. Another important concept is about seccomp profile. First of all, seccomp is a security feature that resides on the Linux kernel. And the seccomp profile is basically a list of syscalls that you can use to put them into a rule and attach this rule to a program by defining if these syscalls could be executed or not by the program itself. So it works as a firewall for system calls. Additionally, it is extensively used in the Kubernetes ecosystem, especially when you enable the seccomp default feature flag. So this means that all the workloads that you are going to run will be attached to this default profile. That is a default seccomp profile that have inside the most dangerous syscalls that you should never use in your run. Let's see now the main idea that I had during the tasks. So the main thought that I had was to generate a seccomp profile as an artifact at the end of a test pipeline. Why specifically the test pipeline? Because in the test pipeline, we are testing as much as we can our code through the test that we write. And depending on the percentage that cover our source code, we can rely on them for a security profile. So if we are testing the 70% of our code, the syscalls that we are going to extract on the test pipeline will be reliable for the 70%. So that was the main idea. Additionally, this seccomp profile could be used in different ways. The most common that came into my mind was to use it through an init container when we deploy our application. The init container basically inject the seccomp by downloading it from the artifact registry and store it into the Kubernetes node in order to allow the application container to load it and run with it. And there's the example. So the init container basically download it and store it under varlib kubelet seccomp. And then the container, in this case, the nginx container, for example, uses the security context seccomp profile of type localhost by referring to the seccomp profile itself with the localhost profile. So now that we have the main concept in our mind, let me explain you what was the step that I followed and how I tried to achieve this goal. So in this image, you can see basically a call graph of an example program. So having that in mind and having all the tests that are rendered can basically understand what is missing and what is not. So we have a general overview about the potential syscall that you are missing if you are not testing the binary. So in order to extract the syscalls from the test, with the integration test, that was the easiest part. What we have to do is to build the binary, provide some script to check for the expected result, general scripts for the integration test. An example that I really appreciate is the test script suite. And basically, we can run our binary by using strace or perf or whatever you want. So in this case, we can collect all the executed syscalls from the binary by testing all the possible branches that the execution has. So this was the first part, but it was not enough in my opinion, because we were missing the unit tests that are such a big part of the test pipeline. So how I tried to extract also the syscalls from the unit test. First of all, it's quite simple to say, but it was a bit more complicated. First of all, the go test command, we have to think that the go test command compile and run the test binary all at once. So when we run go test, we are basically compiling the test and then automatically run with the same command. At first glance, we couldn't do strace of go test because we were going to trace syscalls that were not related to our specific test, but syscalls that were included in the go test command that were out of scope. So what we could do, at first I thought that we could, for example, compile only the test binary without running it using a go test, but running it separately. So if we basically type go test-c, we could compile the test binary and run it by ourselves. The problem in this case is that even doing a strace of the test binary, we could include some noise that are not related to our specific function that we are testing. Because, for example, we can include some function that load some test data from the environment. So as an example, we could open a file, read the file content, and these syscalls will be collected by a strace, but we don't need that. We should try to find a way to avoid this kind of noise. My personal idea, I don't know if it's the good one, but it seems to work, at least in some cases. But the main idea was to create, using a BPF, to define a trace point that basically start tracing the syscalls when a uprobe that is attached to the function that we want to trace inform us that the execution of the function started. And we can stop the trace point when the uretprobe informs us that the execution of the function is finished. So we have a range of time that we can rely on in order to collect the syscalls that derives from our function. An additional information is that Harpoon was based on GoBPF at the beginning, but then I moved to libbpfgo, and I will explain later why I took this decision. So let's see the juice part. So in order to run Harpoon, what we have to do, we should basically build the test binary first, as we were trying to do before. So just typing go test-c, followed by the package path that hosts our function. So in this case, we are going to build the test binary. So as a result, we're going to have a binary that will execute the test where our function is located. Consequently, we have to extract from this binary the symbol name of the function that we want to trace. So in the example, I typed my function. So my function is the function that we want to trace, and we are using obj dump /sims followed by the name of the binary test by graphing for the function name. In this case, we are going to find the symbol of the function name. So as you can see in the example below, so we are doing the obj dump to a test binary of mine. It was an independent project from this talk, and we are graphing for the function interface exist. So interface exist is a function that I've created in my personal project, a Go function that we can find on the binary, on the test binary, with the following name. So github.com/allegro91/forward_ctl/packages/iptables.interface_exists. So once we have the symbol name of the function, we can use harpoon in order to extract the syscalls from the binary. So by typing this command, harpoon-fn, to specify the symbol name of the function, followed by the command for the test binary. So as I explained before, what is going to happen with harpoon is that harpoon will take the elf binary, so binary.test, and will attach a uprobe and a uretprobe to the main.doSomething in this case, but whatever is the name of the symbol of the function, and will, after it attached these probes to the function, will basically run the binary, and the trace point will be informed by the uprobe and the uretprobe about the starting and the end of the function itself. So in this limited range of time, we are going to extract the syscalls. And here it is an example. So by typing harpoon -fn followed by the function, the symbol name of the function, followed by the command of the test binary. So /iptables.test. So here's the list of the functions that are related only to the function interface exists. Let's see now the worst part of this project. Everything was looking nice, but at some point I realized that not all the things were working properly. Main thing that was not working properly was that the uretprobe sometime was not informing the program that the function was returned. What was the problem? Basically, the uretprobe overwrites the return address of the probed function with an address of a trampoline. This trampoline is basically pointing to our eBPF program. So once the eBPF program is executed, and after its end, the instruction pointer should restore to point to the next instruction. But this thing doesn't happen all the time, since the stack in the Go binaries dynamically changes due to the garbage collector, for example. So this kind of behavior could cause the program corruption. So I had to find a way to solve this issue, and luckily for me, I found this workaround on internet. So the workaround consists in starting from the fact that the uprobes could be attached to a specific offset. So we don't need to attach the uprobes only on the symbol function names, but we can do the same to a specific offset in the function, in the binary function. So in order to simulate the uretprobe, what we can do is of adding for each ret instruction that is inside the function a uprobe that basically simulate the functioning of a uretprobe. So instead of attaching one single uretprobe in the function, we can add one uprobe for each ret instruction within the function that we are tracing. And the rest of the function is the same. So benefits of moving to libbpfgo. So at the beginning, when I introduced the harpoon, I mentioned the thing that was based on GoBPF, that is a library from IOVisor, from the IOVisor organization, and that is using a BC under the hood. So now I decide to move to libbpfgo, mainly because libbpfgo gives you the ability of attaching the uprobes to specific offset, and this thing was not supported by GoBPF. So we can basically simulate the functioning of a uretprobe by attaching the uprobes to the ret instructions thanks to libbpfgo. And the use of libbpfgo makes the project even more distributable, easily distributable, because the libbpfgo is a library that is a wrapper of libbpf. So libbpf gives us the ability to write the program with Cori. Cori means compile once, runs everywhere. We don't have to build the binary every time we run the application as we did before with GoBPF that was based on BCC that needs GCC as a dependency to do this thing. So this time we can simply compile the binary the first time from the pipeline, for example, and then distribute the entire program through the repository. So the talk is almost finished. I just want to point you to some links that helped me a lot understanding this problem, and links from which I learned a lot. I also want to thank some people that helped me during this project. Thank you for your attention, and I hope you enjoyed the talk.